Okay, we are... No. Okay, we are starting 6/8, and we're going to be spending 2 days here. And we are back to limits, and we haven't done limits since the beginning of the year. But before we get into it, we need to review what the indeterminate forms were that involve the infinities and the zero. And you are more than welcome to write these on your blue sheet if you want. And remember, an indeterminate form just means that there's more than one solution to these. So it's 0 divided by 0 is indeterminate. The solution can't be determined. Infinity divided by infinity. 1 to the infinity. 0 to the 0. Infinity minus infinity. Infinity times 0. And infinity to the 0. So all of those are indeterminate forms. Solution can't be determined. Our non-indeterminate forms, just a quick review, we do have solutions to these. So they are determinate forms, I guess. Made that up myself here. A number divided by 0. So remember, think of something big. How many times can something almost non-existent fit into it? That equals infinity. A number divided by infinity. So think something kind of big, but something absolutely enormous trying to fit in. How many times does it fit in? 0. And the third one, infinity divided by a number, is still going to be infinity. So these there are solutions to, these there are not. There's multiple solutions to a lot of those. So, now back to limits. What we're going to use today is called L'Hopital's rule. That's an L. That's L'Hopital. I know it looks like the hospital, but it's L'Hopital's rule. And what he said was, if the limit as x approaches c of a function divided by another function, so you have a fraction, if this takes on an indeterminate form, if the limit is indeterminate, then this limit as x approaches c of f of x over g of x will equal the same limit as x approaches the same c of f prime of x over g prime of x. So what he's saying is you can take the derivative of the top and the derivative of the bottom separately, and now when you plug your c into that, if you get an answer, that will be the limit of the original function before you took the derivative. So, very big rule here. This is not a quotient rule. This is not what L'Hopital is doing with derivative. He's just saying do the derivative of the top all by itself, do the derivative of the bottom all by itself, plug your c into the derivatives. If you get an answer, that value over here is the limit of the original one. So, kind of a powerful rule there they found. So this first one, I'm going to do the limit by graphing, and then we're going to do it algebraically. So I'll show you one by graph. I think you might have one in the book. But our goal is to find all these limits algebraically. We want to know the limit as x approaches 1/2 of the natural log of 2x over x squared minus 2x plus 3/4. Well, let's just plug the 1/2 in and see if we can get lucky here. So if I plug the 1/2 in, I get the natural log of 2 times 1/2 is 1. Down here, I'll have 1/2 squared is 1/4. 2 minus 2 times 1/2 is a minus 1. plus 3/4. The natural log of 1, if you remember, e to what power gives me 1? That's the 0 power. So 0 would be the exponent. Here I've got a 1/4. Minus 1 is a negative 3/4, plus I got 0 over a 0. I've got one of my indeterminate forms. Okay, so let me see graphically what this limit looks like it should be. So I've already taken the time. Natural log of 2x divided by, in parentheses, the denominator, x squared minus 2x plus the 3/4. Set the window up because I'm approaching a half. So I just made the x go from 0 to 2 and the y negative 5 to 5. And this is 1 because I put the tick mark at 1, so I'm looking at what's happening at a half. There's obviously a hole in the graph here that's not showing up because I did get 0 over 0, so there's a hole here. But remember, a limit is the y value. What's this y value? It looks like it's at 2. If I go into the table set, if I have it start at a half, 0.5, and I have it go by 0.1s, I can see what's happening before and after. So as I approach the half, I'm at negative 2.1, negative 2.0. There's my error. There's the hole in the graph. Negative 2.0 again. So it looks like I'm jumping over a negative 2. So graphically, it looks like the limit's going to be negative 2. Let's see if we can get that algebraically. Okay, so I did get an indeterminate form, so I can apply L'Hopital's rule, which says this limit, and you do have to carry this along, is the same as the limit as x approaches half of the derivative of the numerator. So I forget about the denominator for now. Derivative of the top, derivative of natural log is 1 over 2x, times by the derivative here is a 2. The bottom, derivative of each term, that'll be 2x squared, minus 2, and that goes to 0. Now when I plug the 1/2 in, let me simplify this here. Let's cancel. So if I plug the 1/2 in, I'm going to have 1 divided by a half. That turns into 2. Let's see, 1/2 squared is a quarter. 2 times a quarter, let's see, 2 times 1/4. Oh, this was supposed to be x. 2x is the derivative, so 2 times a half is 1. Minus 2 is a negative 1. 2 divided by negative 1 is a negative 2. So this time I did get an answer, not an indeterminate form. And there's my limit. Okay, so L'Hopital's rule, kind of powerful. Number 2, the limit as x approaches 0 of sine x divided by x squared plus 2x. If I plug the 0 in, the sine of 0, we'll have to see what that is unless you remember it from last year, and then 0 squared plus 2 times 0. The sine of 0, if you remember, is 0. It starts at the origin. Sine starts on the origin and then goes up, so that is 0. Cosine of 0 is a 1. So indeterminate. So I can apply L'Hopital's rule. As long as I've got one of the indeterminate forms as a fraction, so it's got to be this one, this one. Those are the only two that are fractions. I have to get into fraction form to do it. So it is the same as the limit as x approaches 0. I do have to carry this along. L'Hopital said I can take the derivative of the top, which is cosine x, divide by the derivative of the bottom. This time it's 2x plus 2. Now I plug my 0 in. Cosine of 0 over 2 times 0 is 0 plus 2. Cosine of 0 is 1. If you need to type it in the calculator, over 2. So my limit is a half. And we could have looked at the graph to see that as a check, but it is a half. Okay, let's go the limit as x approaches infinity of 3x squared plus 2x minus 5 over 5x cubed minus 3x plus 8. Okay, plugging the infinity in here. Infinity squared plus infinity minus 5, obviously infinity. Infinity cubed minus infinity, infinity. Indeterminate. I can do L'Hopital's rule. I will get 6x plus 2 over 15x squared minus 3. Plugging infinity in here, 6 times infinity plus 2 is going to be infinity. 15 times infinity squared minus 3 is still infinity. I got an indeterminate for a second time. Well, L'Hopital said all I got to do is do the derivative of the top and the derivative of the bottom. So I get to keep going until I get something. So you can apply L'Hopital's rule as many times as necessary, as long as you're going to get an indeterminate over here. So derivative of the top is 6. Derivative here will be 30x. I'll plug in infinity. I'll get 6 divided by infinity. There is an answer to this. 6 divided by infinity is, how many times does something super, super big fit into something not so big? 0. So the limit was 0. Okay, last one's a little tricky. Tomorrow they'll be really tricky, but so enjoy today. We've got the limit as x approaches infinity of x squared e to the negative x. Well, here I've got infinity squared, which is infinity, times e to the negative infinity. Well, e to the negative infinity, think about that as 1 over e to the infinity. Because remember, negative exponent just brings it down. That's an infinity there, e raised to that. A number to infinity is going to be infinity. 1 over infinity is 0. So what I've got is infinity times 0. Okay, that is one of your indeterminate forms, but that doesn't help me because I don't have a fraction here. L'Hopital's rule only works if you have a fraction. So I need to be able to rewrite this so that I can make a fraction out of it. And I think you can see where this is headed. This negative exponent, if I stick it down in the bottom of a fraction, it becomes happy, and I've got a fraction to work with. So I'm going to go with x squared over e to the x. Now when I plug in the infinity, I get infinity over e to the infinity is still infinity. I get infinity over infinity, that's indeterminate. So you do have to show this indeterminate form, how it comes out, and then you can apply L'Hopital's rule. Derivative of the top is 2x. The derivative of e to the x is itself, multiplied by the derivative of the exponent, which is 1. So plugging in infinity, I get 2 times infinity over e to the infinity. That's still infinity over infinity, indeterminate. Do L'Hopital's rule again. Derivative of the numerator is 2. Denominator is e to the x. This time 2 is going to stay at 2 over infinity. How many times is infinity going to fit into 2?